In this video, we will discuss eigenvalues and eigenvectors. These are incredibly important to solving differential equations in this class. The video will recall some of the basic definitions from linear algebra, and then we'll go into some examples about how these ideas will be used in class. We begin with the definition of an eigenvalue. So given a linear operator L on a vector space V, a scalar lambda is called an eigenvalue of L if we can find a non-zero vector x such that L acting on x is equal to lambda times x. The vector x is called an eigenvector associated with the eigenvalue lambda. The idea behind eigenvalues and eigenvectors is that there is a vector such that when L is applied to it, the vector does not change, except possibly to be scaled, that is stretched or shrunk in some way. But in general, the vector stays pretty much the same. For an example, let's consider this matrix. We can easily verify that this matrix has an eigenvalue 3 associated with the eigenvector 1, 1 by simply multiplying the matrix by the vector 1, 1 and seeing that we get the vector 3, 3. We can also show that this matrix has an eigenvalue -1 associated with the eigenvector -1, 1. When you consider the eigenvalue and the eigenvector together, we'll often call them an eigenpair. So this matrix has two eigenpairs. Being able to find eigenvalues of a matrix is not really going to come up a lot in this class, so I'm not going to go into the details of how to find eigenpairs. Of course, you can go back to your linear algebra notes to try and remind yourself. For another example, let's consider a different linear operator, that is, the differential operator. So this operator acts on the space C1, and it's defined by L acting on the function u returns the derivative of u. All right, one of the simplest differential operators we can come up with. For operators acting on a function space, we often call the eigenvectors eigenfunctions. It's the same basic idea, but since it is a function as well as a vector, eigenfunction seems to make a little bit more sense. So we are looking for a function such that when we take its derivative, we get basically the same function back, except for possibly a constant out in front. So pause the video and take a minute to try and think of such a function. I'll give you a sec. So one such function is the natural exponential function, e to the x. This, in fact, will give us e to the x back after we differentiate. So it has an eigenvalue of 1. So L has an eigenpair, which is an eigenvalue 1, and an eigenfunction, e to the x. In general, we can actually find infinitely many eigenpairs that look like this by considering the function e to the lambda x. When we differentiate, the lambda comes down in front through the chain rule, and we get that L acting on e to the lambda x is equal to lambda times e to the lambda x. So we get an infinite number of eigenpairs, lambda, e to the lambda x, for any value of lambda. This is a really interesting difference from matrices. A matrix only had a finite number of eigenvalues, as many rows as the matrix had. Whereas for this differential operator, we have just found an infinite number of eigenvalues and eigenvectors. Recall that the transpose of a matrix takes the ij component of the matrix and changes it with the ji component. As an example, let's consider the matrix A, which is 1, 6, 4, -2. The transpose of this matrix is given by flipping the off-diagonal elements. So we get the matrix 1, 4, 6, -2. While it is generally easy to find the transpose of a matrix, we will be considering more complicated linear operators that use derivatives, so we need a different way of discussing the transpose. It turns out that the transpose can also be defined by using the inner product. Given a matrix A, the transpose of that matrix will satisfy the following equation for all vectors u and v. And so this equation is stating that the inner product of AU with V is equal to the inner product of U with A transpose V. Remember that AU and A transpose V are both vectors themselves. So this is really just the inner product of two vectors with each other on either side of this equation. A matrix is called symmetric if it is equal to its transpose. Using our inner product definition of transpose, this means that a matrix is symmetric if it satisfies this equation for all vectors u and v. Here we have simply replaced A transpose here with A, since A and A transpose are the same thing. There are three very important theorems regarding symmetric matrices and symmetric linear operators, as we'll see later. While these theorems are stated in terms of matrices, we will see that they apply to other linear operators as well, and in particular, differential operators that act on functions. The first theorem says that all eigenvalues of a symmetric matrix will be real, and also that the eigenvectors will be real. The second theorem states that for a symmetric matrix, if we consider two eigenvectors that correspond to different eigenvalues, so x1 and x2 are eigenvectors that correspond to different eigenvalues, then x1 and x2 will be orthogonal to each other. And this is really interesting, the fact that the eigenvectors of a symmetric matrix kind of point in perpendicular directions or orthogonal directions. And finally, we can combine all of this and get really the big one. It's big, because it gets a name. The spectral theorem for symmetric matrices. It says that a symmetric matrix that is n by n, that is a symmetric matrix that acts on vectors in Rn, then the eigenvectors of that matrix will form an orthonormal basis of Rn. This makes finding the eigenvectors of a symmetric matrix a very useful problem to solve, as it gives us a nice basis of Rn to use.